In this tutorial, we will consider stability checks on a simplified pressure vessel. We click on the Add New Vessel button. We input a simple name. We select Vertical Vessel Orientation. We move on to the Process Data tab. We fill in the process card input data. We move on to the Vessel Desktop tab. This vessel will contain a cylindrical shell and two heads. We input a simple name and description for the main shell. We move on to the Design Data tab. We see that the process card data is automatically filled in. We move on to the Shell Geometry Data Input chapter. We fill in the geometry data of the main shell. We move on to the Material Data Input chapter. We leave the material as it is and move on to the Component Liquid Input chapter. We select to fill the main shell completely with liquid. We click on Calculation Details to save the main shell. Now we are going to add the top head. We click on Ellipsoidal Head. We input a simple name and description. We move on to the Component Attachment tab. We leave the attachment location as is and move on to the Design Data tab. We move on to the Head Geometry Data Input chapter. We input the head geometry data. We select carbon steels with C less than or equal to 0.30% for the modulus of elasticity. We leave the material as is and click on the calculation details to save the head. We exit back to the vessel view. Now we will add the bottom head. We click on Ellipsoidal Head once more. We use component dimensions just like to copy all the data from the top head. We move on to the Component Attachment tab. The attachment location is automatically set to the correct point. We move on to the Design Data tab. We will add liquid to the bottom head. We choose to fill it completely by clicking the Full button. We exit back to the vessel view. Let's have a look at the 3D view of this vessel. Notice that this is a typical pressure vessel containing liquid up to the end of the main shell. The vessel will be considered for wind and seismic loads, but before we accomplish that, we need to prepare the wind factors by clicking on the Wind Factors button. We can quickly apply the same shape factor to all components by selecting the Entire Equipment option. We input the CF shape factor and DW diametral increases values and click on Save. This will give the same wind factor and area increase to all the vessel's components. We move on and click the Wind button. We select the EN 199111 wind code. We leave the preset values as they are. We click on Save to apply our changes. We move on by clicking the Earthquake button. We select the EN 19981 seismic code. We input the desired value for seismic. And click on the Save button once we are done. Now we will create the correct load cases. We click on the Load Cases button. We choose the Classic Pressure Vessel Load Case Ready scenario. We remove all load cases except for Operation Wind Corroded and Operation Seismic Corroded. We click on the Save button to save our load cases. We click on the Run button to run the vessel calculations with the new load cases. Let's check the weight of the vessel through the Print button. We print a Weight and Centre of Mass report. We see the weight and centre of mass only for the dedicated 2 load cases we have saved. If we had included more load cases, they would be present here. In order to perform stability analysis, we need to include a component that can cause that analysis, like a skirt support, bracket support, legs, etc. We choose to add a leg support. We input a simple name and description. vClavis allows the user to connect leg supports on a head as well as a shell. We choose to attach the legs to the bottom head. We move on to the Design Data tab. We fill in the leg input data. We move on to the leg geometry data input chapter. We select the Check of Baseplate calculation option. We leave the baseplate evaluation option. We click on Pipes Libraries for the leg dimensions. We choose nominal size 4-inch legs. We move on to the baseplate and anchor data input chapter. We select the square baseplate type. We fill in the baseplate dimensions. We move on to the Load Cases input chapter. Here we see that the legs have the corroded option for both load cases. We input the modulus of elasticity for both load cases. We add a new material to the legs. We search for SA106 Grade B. We leave the rest of the materials as they are. We see that the legs did not pass some checks. We see that the fail is on the contact of the legs with the head. We also see that we need to increase the thickness of the base plate. We see that the utilizations exceed 100% on the seismic load case. Let's make a few changes to our input. We increase base plate thickness to 20 millimeters. We add a reinforcing pad through the calculation options. We fill in the geometry data for the reinforcing pad. We click on the calculation details to save our changes. Now we see that all checks have passed successfully. Let's have another look at the 3D after we added the legs. Let's have a look at the detailed calculations for the legs through their PDF report. In this report, we can see a detailed analysis of all our inputs and calculation results. Notice that a few issues in the geometry's design are marked as warnings. Notice that there are forces applied directly to the legs. These forces are a result of the analysis in the wind and seismic load cases. In order to verify the resulting forces applicable on the legs, we can reveal the primary stability analysis, which is performed via the vessel stability checks. We click on Vessel Stability Checks. Note, vessel stability checks must be performed on tall vessels, because this is how all cylindrical shells are checked against bending moments, buckling loads, etc. We see that the data for the load cases is automatically filled in. Here we see all resulting data for the wind profile up to 200 metres. We see that until 5 metres, we have about 1.7 kPa being applied to the vessel. Let's have a look at the seismic data next. This is the entire horizontal and vertical seismic spectrum. Notice that we get a relevant G loading based on the intrinsic frequency of the vessel. Next, let's check out the calculations for the wind-corroded load case. Notice the forces that apply due to wind in the components wind data table. Notice that AW in the wind data table also includes the shape factor taken into account. Wind forces are divided by the section component length, and wind linear shear load is applied on the vessel. Here we can see resulting stresses based on the maximum principal stress criteria. Each code equivalent stresses are calculated accordingly. For each load case, calculated deflection and natural period of vibration are shown herein. Here we see a typical vessel stability graph for the wind-corroded load case. Moving on to the next load case, in the seismic accelerations table, we see the acceleration value, G loading, that is calculated through the intrinsic frequency of the vessel for the applicable seismic spectra, shown above. Let's have a look at the stability graphs for this load case. We exit back to the vessel view. We have completed a stability check of a vessel. Be sure to always run the vessel stability checks after the calculations of supports, legs, saddles, skirts, etc.